In this chapter, we're really starting to focus on how we actually do map making and transform the three-dimensional globe to a two-dimensional Earth that we represent on a surface. There are several different objectives that are covered in this chapter, such as including the concept of map scale and how it affects map projections and how we draw map projections, how we specify geographic locations using coordinates, how we convert those coordinates, how we explain the concepts of how we understand the shape and size of the Earth and use that information to make coordinates for mapping, how we recognize different kinds of transformations that we need to use in order to register locations and data sets, how we describe the characteristics of different coordinate systems, including the UTM coordinate system, the state plane coordinate system, and then also look at different types of map projections, and there are distortions that can happen through geometric transformation. We then talk a little bit about how we classify projected map graticules by projection family. First of all, I want to draw your attention to the concept of map scale. So in Chapter 2, the textbook gets a little bit more into detail coordinate systems. I wanted to look specifically at how we go about drawing map scales on maps themselves. And keep in mind that we have three different ways that we can express scale. One is known as a verbal or written scale, which is where we explain a relationship between the distance on the map and the distance on the ground. For example, 1 inch represents 1 mile. Or we could do it with a bar scale. A bar scale is a graphical device where you draw the distance on the bar scale. As you zoom a map in or out online or in another digital format, the bar scale will change scale along with the map, and that's a great advantage of a bar scale on a map. The variable scale is used when we have a map projection that leads to a map where scale is not consistent across the entire map. In order to depict the surface of the Earth, we need a way to take locations in two-dimensional space and convert them from their representation on the globe to a representation on the map. And we do this through using a coordinate system. And the basis of coordinate systems come from Cartesian coordinate systems. We'll talk a bit about how we use geographic coordinate systems, such as longitude and latitude in GIS mapping as well. First of all, a geographic coordinate system is a coordinate system of projections. As I mentioned, coordinate systems are important because we're attempting to go from a three-dimensional Earth globe to a two-dimensional flat surface. And one of the ways we can represent a flat surface in 2 dimensions is by using a Cartesian coordinate system. Under a Cartesian coordinate system, we have a point of origin in the center of the map, or of the coordinate system in this case. We represent that by an x-axis, which is our horizontal axis on this map, and a y-axis, which is the vertical axis. The Cartesian coordinate system results in a central point of origin with negative values as one moves to the left and positive values as one moves to the right, and then positive values as one moves up on that coordinate system and negative values as one moves down. It's not very hard to take that type of system and apply the latitude-longitude concept to that with parallels and meridians, where parallels, for example, the equator, would be represented as the flat line across the center of this diagram, where if you were to go to the west along the equatorial line, you would be going to the left, and that's represented as a negative value, whereas to the right is represented as a positive value. This is the result of the geographic or geodetic coordinate system that uses latitude and longitude. Again, this globe is another way of representing a simplified version of a three-dimensional space where we can see the point of origin in the center represented by what we would assume to be the equator and the prime meridian. We've already looked at latitude and longitude in another lecture, and I'll refer you to that one for more information. This is another view of latitude and longitude as we see it at work in this case, Google Earth. Latitude, again, the angular distance north and south of the equator, and parallels are lines connecting points of the same latitude. Longitude is angular distance east and west of the prime meridian, and meridians are lines connecting points of the same longitude. We measure and indicate latitude and longitude using a system that goes back to the Babylonian sexagesimal system. Thus, we talk about latitude and longitude in degrees, minutes, and seconds. So, for example, we would describe the location of Cleveland as being 41 degrees, 28 minutes north, and 81 degrees, 37 minutes west. Salem, Oregon, on the other hand, would be 44 degrees, 56 minutes, and 18 seconds north, and 123 degrees, 1 minute, and 47 seconds west. South and west locations may also be expressed using the minus sign as opposed to the directional notation. And north and east locations may be expressed using positive sign. We can also express locations in latitude and longitude using decimal degrees, where we're looking at decimal degrees representing a share of 60. If you were to convert this from minutes, seconds, and degrees into decimal degrees, you would start out by recognizing that there are 60 degrees, 60 minutes in a degree, and 60 seconds in a minute. So therefore, you would, for example, express the location 44 degrees, 56 minutes, 18 seconds as 44 plus the result of 56 divided by 60. So 56 minutes is very close to 60 minutes. And then we would also add the number for seconds, which is a ratio of 3600. So in this case, 18 3600ths. So we would say 44. We then put our decimal point in place, and then the result of 56 60ths plus the result of 18 3600ths. That gives us a result of 44.9381. With the advent of GPS units and GIS technology, more and more we use the decimal degree system to express latitude and longitude locations rather than degrees, minutes, and seconds. Sometimes you'll see it expressed in either way, and an awareness of what those numbers mean is useful. You can obviously find all kinds of tools online and apps on phones and so on to convert back and forth if you need to. The concept of latitude and longitude largely depends on being able to define that point of origin. In other words, we know where the equator is, and it's the point that's halfway between the north and south poles. But what about the prime meridian? We don't have an east and west pole, so there is no central point. The prime meridian is just an arbitrary measurement. Prime meridians go all the way back to Eratosthenes, who had declared that Alexandria would be a prime meridian useful for the Greeks to be able to map out and use a grid system to measure distances, in this case east and west, from Alexandria, which was a major trading center in the Greek Empire. Early in the history of the United States, Thomas Jefferson suggested using the White House as a prime meridian, and it shows up as a prime meridian in early 19th century maps. Prior to independence, the United States had been using the British system, and of course at the beginning of the history of the Republic, the United States attempted to get away from things that were British. And so that became a way that we could express that independence and use it for our own purposes. Many countries around the world have developed their own prime meridians. For example, the Persian Empire in the Middle East. China has had several prime meridians in the past, as has Japan. But at the International Meridian Conference in 1884, an international standard was agreed to as the British prime meridian became the standard location of the prime meridian. And that's why the prime meridian is where it is today. The result of the conference was that the major countries of the world agreed to the principle of time zones. With the change in technology in the 19th century and the advent of telegraph machines and teletype, as well as trains and faster steamships on bodies of water, all of a sudden there was a need to regulate our understanding of time. So around the world, people began to be interested in creating a single time chart to be able to connect places together faster and better, as opposed to having, for example, each county determine its own time, or each village in the case of older countries in Europe. The result is a time zone system that's based on the idea of 24 hours in the day, therefore 24 time zones. If you divide 360 degrees in the circle by 24 time zones, you get 15 degrees as the result, which means that in theory, there is a new time zone every 15 degrees. In reality, as you can see on this map, the impact of longitude on time zones only goes so far, and countries choose to be in the time zone they want to be in for economic and cultural and other reasons. I want to draw your attention to a couple of interesting patterns here on this time zone map, where longitude becomes less important than cultural and economic traditions. For example, if you look at South America, you'll see that eastern Brazil is in the same time zone as Argentina, even though Argentina is directly south of Brazil's second central time zone. And so what this is about is the economic relationships between southeastern Brazil and the country of Uruguay, as well as northeastern Argentina. China has one time zone for the whole country, even though China is the same distance from east to west as the United States. And so on the east coast of China, it could be getting light in the morning at 7 a.m. or 8 a.m., while meantime it doesn't get light until 11 o'clock or noon if you're on the far western edge of China along the border with Kyrgyzstan or Tajikistan. Other examples of anomalies are Australia, which has a time zone where time is separated by 1/2 hour. So there are all kinds of different ways that countries will manipulate time zones for their own purposes. So again, the time zone system was established in 1884. There are 24 time zones. Each extends longitudinally by about 15 degrees. All of this is centered on Greenwich Mean Time, which corresponds with. Next, we'll shift into looking at how coordinate systems are actually used in mapping, starting with the Universal Transverse Mercator Coordinate System. This coordinate system is based on dividing the Earth up into 60 different grid zones. The portion you can see on this particular slide shows how this grid system is divided up within the United States, lower 48 states, and the vertical lines represented on here represent meridians of longitude. For example, you can see there that most of Ohio is in zone 17, but a little bit is in zone 16. And as you move further to the west, the zone numbers drop. We'll see examples later in the semester about how the UTM coordinate system is actually used. For example, it is the main coordinate system that's used in satellite imagery when you look at Earth observation systems. So having an awareness of what the coordinate system is you're working in and how to convert it from one coordinate system to another can be very important when you're looking at combining different types of geospatial data, such as Landsat data from the U.S. Geological Service and NASA, with other types of data, as we'll see some examples, and I'll mention some that you might want to combine with that as we go along. This shows the results of coordinate systems on a USGS topographic map, similar to the maps you worked on the assignment during the first unit. And so this shows evidence of several different coordinate systems, such as latitude and longitude, state plane coordinate systems, which shows you the 1,970,000 feet line, for example, versus UTM coordinates, which shows you in the lower right-hand side of the image, the 2 with the mark 59 is a representation of the UTM system. A particular type of map projection is used to show the 60 UTM coordinate systems. Each is divided into north and south halves at the equator, and here you can basically see the result of this represented on a world map. One of the unique features of the UTM coordinate systems is that they use a unique point of origin system, which is intended to simplify the reading and meaning of these particular coordinates. We won't get into that in any more detail at this point, but it's something that you may see reference to later on this semester. The basic idea is that there's something called false easting and false northing, which is a way of representing locations not starting at a 0 or negative point, but in fact representing it with a meter grid system. And as you move to the north from the equator, every meter increases 1 digit in this grid system. State plane coordinate systems have a completely different representational style and use. The UTM system was designed to meet the need for coordinates to specify geographic locations globally. But if you look at local conditions, one of the important things that you'll find out about mapping is that because the Earth is not a perfect sphere, local conditions can vary. So in the United States, it was realized that it would be useful to have a state plane system with the advantage of having a local coordinate system that's meant to be highly accurate for mapping within that particular part of the world. And so plane coordinates were devised for that purpose and were placed onto a map of the United States. All of the values in the plane coordinate system are positive, as opposed to what we saw with the Cartesian coordinate system, which has negative values as you go west of that particular point of origin, or north or south of that equator or point of origin across the horizon, the horizontal line. And also, one of the benefits of state plane coordinates is that they're highly accurate. So they have a maximum error rate in terms of locations. That is the transformation from the spherical Earth to the flat surface of only 1 part in 10,000. In other words, for every 10,000 inches, the allowance of error is only to have 1 inch of error in terms of location. This map shows U.S. state plane coordinate systems as of 1983. The 50 states of the U.S. are divided into 124 state plane zones. Ohio is divided into 2 zones, Ohio North and This slide shows the example from Pennsylvania, which is also divided up into a north zone and a south zone. Specifically, the standard lines of the map, which is the most accurate area of the map, basically shows you where the map is at its most accurate in terms of how it's drawn. This results from something that we will look at a little bit later in the chapter as we go through. But suffice it to say that state plane coordinates are very useful because they represent a mapping that is highly accurate, it's locally derived to the local conditions, and it also represents all values in positive numbers. And that concludes this section of the lecture.